let us now take an example and design a transformer for a DC-DC converter. I have taken here an example of a forward converter where we have discussed its operation and we know how it works. So let us say we have an output voltage spec of 12 volts, output load current as 3 amps, switching frequency of 20 kilohertz, input Vi as 24 volts plus or minus 10%, and then we need to design this transformer. So let us see how we go about doing that. So step 1, we need to find what is the output power. Output power is V0 I0, but we need to find what is the power at the secondary here. So if you see the secondary, because P0 here refers to, when you're talking of design of the transformer, all the power right at the point of the secondary terminals. So you see this is the power here, V0 into I0, and in principle the components are not ideal. There will be a diode drop, especially at higher powers. The diode drop here will be around 1.2 to 1.5 volts into I0 that will come in here, and then there will be resistance, winding resistance, and there will be some drop in the winding resistance. So put all that together, you can increase V0 by 10% and add the VD drop. So what we can do is we can say 1.1 V0 plus VD will be the voltage that will be needed here to take care of output V0 of 12 volts. So this will give us a slightly higher voltage at the secondary, so that all these drops are taken care of. Into I0 will be the power at the terminals of the secondary. So apply V0 12 volts, VD of 1.5 volts and 3 amps, you will get around 44.1 watts. So for this secondary output power, we need to design the transformer. Next step is find the area product. So the area product for a forward converter, we have derived 2.25 P0 by root 2 kW Bm JFS. P0 is what we have calculated here, 44.1 watts. kW, we will take it as 0.4, a conservative value. Actually, the 0.4 is actually a value where the winder is quite experienced and skillful. Bm for transformers, we reduce the Bm. For inductors, we used to take 0.25 Tesla, but for transformers, don't swing beyond 0.2 Tesla because we want to limit the magnetizing current and also to keep the swing within the linear region of the BH curve. Then J, same as before, as you used for inductors, 3 into 10 to the power of 6 amp per meter square or 3 amp per mm square. Frequency, switching frequency 20 kilohertz as given as a spec. Now if you apply all these and calculate, you get 1.4617 to 10 power minus 8 meter to the power of 4. Multiply this by 10 to the power of 12, you will get it in mm to the power of 4. 14,617.2 mm to the power of 4. Go to the wire table as before and then search for a core which has a higher AP than this. In our case here, we can still again select P36/22 pot core, which has an area product of around 20,000 mm to the power of 4. AC of 201 mm square, AW of 101 mm square, AP area product of 20,100 meter to the mm to the power of 4, mean magnetic path line of 53.2 mm. So these are the characters of the core that we have selected, pot core P36/22. Next, we go to the turns. Primary number of turns NP is given by VI max divided by 2 AC Bm Fs. VI max is 24 plus 10%, which is 26.4 volts. AC we have found out 201 in 10 power minus 6 meter square, Bm 0.2 Tesla, and 20 kilohertz. On calculation, you will land up with 16.4, set NP as 17 turns. Next, let us try to find out what is the turns ratio. Set Dmax as 0.45. Remember that this is a forward converter. You cannot have a duty cycle more than 0.5. Therefore, set Dmax as 0.45 to be on the safer side. And Vi max Dmin should be equal to Vi min. Dmax should be equal to whatever the output voltage. Here the upgraded output voltage of 1.1 V0 plus Vd. Now using these two, you can find Dmin because Dmax is set. So Dmin is equal to Vi min Dmax by Vi max. You know Vi min 24 minus 2.4, Dmax 0.45, Vi max is 26.4. You can find out Dmin, which is 0.41 duty cycle. Now this 1.1 V0 plus Vd should be equal to our forward converter input output relationship N into Vi max into D min, and here N is the only unknown. We have 1.1 V0 Vd divided by Vi max and D min. You apply the values at 1.35, and Ns is equal to N into Np, which will turn out to be 1.35 into 17, which is 23 turns. So Ns is 23 turns. If you are using a demagnetizing winding, remember demagnetizing winding will be very thin wire because it's only the magnetizing current that will flow through it. It probably will be SWG 45, but you need to use the same number of turns as Np, which is 17. Next step is to find the wire gauge. So I as secondary RMS is, I0 into root D is the current, RMS current that is flowing through the secondary. So I0 root D max, you can calculate around 2 amps, 3 amps into root of 0.45. IP RMS is nothing but N times I secondary RMS, which is 2.7 amps. And calculate the wire cross section of the primary IP RMS by J. J, you take it as 3 amp per mm square. You will end up with 0.9 mm square. Area of cross section of the secondary winding wire, IS RMS by J, you have 0.67 mm square. For the primary, go to the wire table and you will see that SWG 18 will fit. It has a wire cross section of 1.167 mm square, and SWG 19 will fit for the secondary. AWS will be 0.8107 mm square. Finally, come and do the cross check, window area cross check, to ensure that the windings will fit into the core. KWAW can calculate 40.4 mm square, and NPAWP plus NSAWS will be equal to 39.1 mm square. So you see that the window area check is satisfied, and the design of the forward converter transformer is complete.